Thanks, Roger. I must say I spent enough time in France to be very intimidated by speaking in this institution. And it's not just the people I speak, it's also the ghosts, all the people who were here, which really scare me. And everything went wrong. My computer crashed. I'm sure it was Michel Foucault, his ghost, which scares me particularly. So everything went wrong. So let's see. As Roger said, this is joint work with Andrea and Giorgio. I should also say that you can interpret what we're going to do in different. So we're going to take an extreme form of rational expectation here. So I'm not sure it fits. Certainly not with the models this morning. And we're going to have some very absurd results. So you might take this to interpret this the negative way by saying, look, how many crazy things you get by assuming rational expectations. But in any case, so what we want to do is we're looking at models with social interactions. So these are typically models where we're going to look at very simple models, but these are typically models where the utility function in an indirect form, the utility function of one agent depends on actions, his own action, and actions of other agents. Maybe his friends, his peers, his parents. It might also depend on some general externality, okay? So it might depend on the average action in some specific population. So this is the kind of model that we're interested in. There's a large literature here, many applications. I'm going to show one particular application that we looked at, which is on smoking, okay? So the main example is smoking. Apparently, we use Mike as a reference point, so let's keep going with Mike. So I have a random shock, which tells me how much I smoke, which is IID, but then I look at Mike, and if he smokes, I'll smoke a little bit more. If he doesn't, I'll smoke a little bit less. And the reason is, of course, I look at him as my mentor, and I try to do whatever he does, okay, or to get close to him. So that's the kind of setup. You see immediately that in this kind of setup, multiple equilibria arise all the time. If everybody smokes and Mike smokes, I smoke. If Mike doesn't smoke, I don't smoke. If this relationship, not in this case, but if this relationship is symmetric, Mike looks at me and does the same. Okay, so multiple equilibria here is a fundamental issue. Now, there are all sorts of other problems in this literature, where by problem I mean if you want to put this literature into data, which is what we're trying to do. So there's all sorts of identification issues that the literature has discussed enormously, from group effects, correlated and observable effects, masking reflection, and so on. Selection problems are crucial because which agents entering my utility function, it's of course not exogenous. So there's all sorts of problems that we're just going to look at multiplicity in some sense, okay? So, by the way, this, again, Foucault, this thing is wrong. It should go the other way, but it doesn't really matter for the example. So, of course, I don't have to make this point. In a model with multiple equilibria, which kind of equilibrium arises is important, okay? It's important for comparative statics, of course, right? So, if we are suppose that we have, and in fact we will, in this kind of model, we will have modulo the fact that it's upside down. We will have one parameter is a shifter of this sort, right? So if we are on the blue line and we go to the red line, well, if we are on the left equilibrium, the small smoking equilibrium, then smoking goes down. If we are in the middle, smoking goes up. Okay, so you might want to think about stability here. You might want to say some equilibria are not stable. It's not very clear with respect to which dynamical system they're not stable. So that's the sense in which I'm saying I'm going to go rational expectation, and I'm not going to worry about some equilibria being less plausible than other because of stability considerations, because I don't have any stability considerations here. And I want to argue that this is an interesting thing to do, and I'll tell you at the end why. Okay? All right, so of course, doing linear models when your world is non-linear is not a good idea. All right, so what we're going to do here, of course, I'm just going to hint at a few things that we do. So we are trying to have a relatively general environment where we can think about identification and we can think about estimations of these kind of models, where when we face multiple equilibrium. Some of the issues with estimation are computational, and so we are going to, I mean, this is not, okay, so we're going to show a way, obvious, natural way where, which helps in the computation, which you can estimate, which you can use to estimate these models. I'm not going to talk about Monte Carlo, and I'm going to have an application to smoking. Okay, so again, maybe this is the slide where, which relates more to the discussion this morning. So what do people do in this literature? Well, some people just seem to be afraid of multiplicity, so they just look at models, impose structure, for instance, linearity, impose structure where you have a unique equilibrium, so they just avoid this. Okay? Other people do make assumptions about equilibrium selection. Okay, so suppose you know you have three equilibria in this economy. You say, well, selection is random, independent. Suppose you observe many periods. For instance, Boy and Jovanovic, Duxford and Jovanovic did this. Right, so static model repeated over time, and you say, look, there are three equilibria. We assume that the selection mechanism is Markov, and we estimate actually the Markov parameters. Okay, so that's one way in which you can think about modeling this. We don't want to do this. What we want to do is we actually want to being able to look at this model even if you don't have variation over time or variation over whatever space, right? So even if we have one single, suppose in this particular example we're going to look at, we're looking at people smoking in a school. Our environment, we have 40 schools, but suppose we only had one. Okay, so our environment is one school. There's a bunch of people in this school. We assume they have these preferences to conform with their friends. And so the equilibrium in general, the model in general will have multiple equilibria. We want to be able to know in which equilibrium they are. Okay, so we don't want to assume that we have variation over equilibria which are played in the economy. Okay. There's a related literature in IO which does some of similar things. Okay, so which kind of a model do we have? Suppose just to fix, again, as I said, we're trying to be general, but in the paper, but just to fix ideas, binary choice, don't smoke -1, smoke 1. This is some, I don't know, again, this is not Foucault, this is Andrea Moro. I don't know why he did it this way, but think of the pie as some kind of a average or aggregate measure of whatever happens in this economy. Okay, so it's more natural to think of pi being the fraction of smokers. Okay, it doesn't change, it's a translation, so it doesn't change anything. So think of pi as the fraction of smokers. So what do these people do? Well, they maximize, they choose smoking. Epsilon are the shocks, the individual shocks, how much they like to smoke. Pi is, think of the fraction of smoker in the economy. Z are characteristics of the school. Xi are individual characteristics of the age, and Yi are the choices. Okay. We are actually looking at a very simple linear model where the shocks have a specific distribution. Now, this is, so this model comes straight from Brock and Durlov. The particular functional forms are the only ones under which you can solve this thing. And so it's not that extreme value, I don't know that extreme value distributions, for instance, are particularly nice for any sense or map particularly this problem. It's just that, you know, you take any statistical mechanics book and in page -1 you find this thing, okay, right in the preface. Okay, so that's what you're doing, and of course, again, page -1 you find the solution. Okay, so the equilibrium looked like an hyperbolic tangent, which is the thing that I was trying to that I had drawn at the beginning, and it looks like this. Okay, so pi on the left, pi on the right, and the first of the conditions is on top. So we're going to look at this model, but we're going to do something else. We are going to look at this model with also local interaction. Okay, where local interaction, what we do is, suppose you take this whole population, in particular in this case it's a school, you take the population of a school and you divide the school into possibly overlapping groups of friends. Okay, so I look at Mike, and Monica apparently also looks at Mike. Okay, so I might be looking at Monica or not, but we have this structure of overlapping groups in the economy, which are small, okay, finite. We are going to essentially assume, as you see here, that the school is large enough so that we can use the law of large numbers. But in these local groups, these are small finite groups of people. Okay, so we can append this extra component where the choice of the agent doesn't only depend on the fraction of smokers, but also depends on the fraction of smokers in this agent's little neighbor, okay, little group of friends. If you do that, then you don't have any closed form solution, and it's kind of complicated. Okay, so but I'm going to say a few things about this. Again, modulo the fact that it's upside down. In the simple model without local interactions, you typically have three equilibria of that sort. Of course, you can also have one depending on the parameter. It might be that this map moves up so that you only have the lowermost equilibrium, okay, or only the uppermost equilibrium in the right one. Okay. So that's so either one or three, and non-generically two. Okay, so this is the case in which we can solve. With local interaction, it's a bit more complicated because depending on the parameter of local interaction, you can have what physicists call phase transitions. Okay, so this is essentially roughly law of large numbers breaks up. Okay, so you might have different distributions over the space, over the geographic space, and it's a little bit more complicated. Certainly, I cannot represent it. Okay. All right. So, in terms of oops, now I'm hooked here. I have to. In terms of identification, sometimes, as I said, people in this literature seem to be somehow not always, but often to be worried about identification with multiple equilibria, as if multiple equilibria kind of mean that identification is harder. And that's not, conceptually, that's not really true. If you in general think very abstractly to a model like this, a situation like this is a situation where you have multiple equilibria. These are data and these are parameters, right? So you pick a vector of parameters, this is abstract, okay? So vectors everywhere. If you have a parameter and you have three equilibria. For every parameter, you have a lot of equilibria. You have three equilibria. But identification is the inverse map. So, if I see the data, there's only one parameter which is consistent with that data. Okay, so what I'm trying to say here is that, again, as I said, we have a very general, somewhat general structure here, but identification, there's no sense in which conceptually the fact that we have in principle multiple equilibria means that identification is harder. Okay, so it's easy to write down a model with a single equilibrium, same thing, parameter here, data. There's a single equilibrium. For every parameter, there's only one equilibria, and it's not identified. For every level of data, there's two parameters. Okay, so the two things are conceptually independent. There's a very nice paper by Bojan Jovanovic in the 80s who does this. It's unreadable, so I think that's maybe one of the reasons why people keep going with this, but it's exposed, it's clear, it's nice. All right, so identification is no big deal. Depends on the particular model, but it's no big deal. Estimation. So the crucial thing is, this is also very straightforward. Okay, so you don't have to look at what the likelihood is. I don't know what that is. But there's an obvious way to think about this model. Okay, which makes the which makes the estimation simple. So the problem here with estimation is, in principle, you don't know how many equilibria you have. In this particular model, if you have only global interaction, you do. But in general, you don't know how many equilibrium you have. So in principle, if you want to construct a likelihood and take into account of the equilibrium condition in the likelihood, you are going to have to compute all possible equilibria. You're going to have to solve for the equilibrium map. Okay? For every parameters, you solve over the equilibrium map, and then you see the likelihood of that equilibrium. That is complicated, so computationally complicated. So the obvious way to go here in estimation is to, in some sense, look at conditional likelihood, conditional on an equilibrium in the sense of an outcome which is achieved. We are essentially assuming here, apart from the numbers from the sampling, if we had an infinite population, we are essentially saying, look, that pi, the fraction of smokers, it's observable in the data. We see what is the fraction of smokers in our school, in each school, right? So we can just essentially estimate first of the condition, conditional on pi hat being the equilibrium which is achieved, okay? And the rest of the model and the rest of the estimation procedure will do the rest, okay? So this in some sense avoids all the complicated issues of estimating all the equilibrium map for each value of the parameters. Once we find the estimated parameters, the C's and the J's, then we can go back and actually simulate how many equilibria we have for that parameter value. And that's easy to do, and that we want to do, and it's interesting to do because, as I said, comparative statistics and everything depends on which equilibrium you are, on the structure of equilibria. But we need only to do this at the estimated parameters. You see, here I added the local interaction, right? So G of I is the group of friends of agent I, pi of G of I is the fraction of smoker in his group, and J is the local interaction parameter, sorry. Okay, so let me avoid selection because I have really nothing to say. So, in the sense that it's a problem, it's there, and there's nothing I can do about it. Okay, so what do I want to do? So let's look at what happens. Okay, so as I said, a good chunk of this paper is methodological. I'm going quickly through it, but a good chunk of the paper is methodological. The idea here is, up to now, what we've done is we have a little model. We can, in some simple cases, we can compute all equilibria. We can characterize the equilibrium manifold. More generally, we cannot because of these phase transitions. Still, we can think about identification in a rather straightforward way. That doesn't mean that identification the assumptions for identification are weak, but they're straightforward conceptually. We can do estimation in a rather straightforward way also. So we're ready to estimate the model and look at it, okay? Now, again, we are estimating the model structure, and it's very crucial that we use those functional forms, which it's a big problem, okay? But we are using those functional forms. Everything we do depends on that functional forms in a crucial way. So, all right. So, okay, identification. So the data is the AdHealth data set. It's very nice. Everybody is using it in this literature because it gives you. So it's 41 schools, which are supposed to be a sample of the US, grades 7, 12. We know essentially everything inside the school, so with AS kids there's a bunch of variables. We are only using smoking, but there's all sorts of other dimensions on which they quiz kids. But crucially, they ask them about their friends. And their friends are typically, most of the times, their friends are in the school. They list their friends are in the school, so we have data on their friends. Okay, so that's what everybody uses in the network literature, and this is a simple case of that. Okay, so we're looking at this data, 45 schools. I thought 41, I don't know why. There's 45 schools, okay? Right, so we have different specification. I'm not sure how important it is, but it's important that one of the things we do is we impose no constraints. So the first specification, if you wish, imposes no constraint on the relationship across schools. It's as if we estimated school by school. Okay, so this is both on the parameters and on the equilibrium. Okay, so we observe each school, we are looking at each school, we get the parameters from each school, and the equilibrium at which these people are coordinated their expectations on. Okay, so the first is this. We estimate a C and a J and another J if there is local interaction for every school. Or, you can impose some structure, and these parameters depends on the Z's are the school characteristics. So you might have the C's have a linear structure, depends on the school characteristics, or they are random, and we make assumptions about their distributions, so random coefficient parameters. Okay, so, or both, or whatever. Huh? So we do this with school-wide interaction only, as well as with local interaction. All right, so this is the case with separate schools. I don't know that this is not, I'm guessing an audience where the numbers matter too much. Not that they matter to me either, but in any case, these are the numbers. So these are the C parameters, mean and median across schools. Okay, so black people smoke less, so do Asians, females smoke more, older people smoke more, smarter people smoke less, and blah, blah, blah. Okay? All right, so the other thing here, as I said, we can have parameters depend on the school characteristics. There might be some interesting stuff that we get off of the structure of this, of the way the estimated structure of the way parameters depend on school characteristics. For instance, female smoking is related to the socioeconomic status in which the schools are. Asian smoking, it's stronger for poor people, for poor areas, and things of this sort. Okay. All right. So one thing that might be of some interest is that the social interaction parameters, how much the utility of an individual depends on the choice of his friends or the choice of the mean. In this case, it's the choice of the mean, or is the mean smoking. Well, that parameter seems to depend a lot on policy variables. Okay, so tobacco training, student policy, staff policy, which if we're going to think about this experiment, this example in terms of policy, then we would worry or think about this, because to us this parameter is actually a utility parameter. But okay, so let me go to multiplicity, which might be more interesting. So the first point I want to make is that we are essentially always, see, it's 41. I don't know what happens to the extra 4 schools. So multiplicity is pervasive. Okay, so in the sense that, again, conditioning on the model, we estimate parameters in every school. In 40 out of 41 schools, we estimate parameters such that at those parameters, when we go and compute the equilibrium map, we have 3 equilibria if it's a global only. Okay? Interesting also, perhaps interesting, I thought this would be interesting in this audience at least, the intermediate equilibrium, which if I had written the concave convex part right, would be the unstable one. So the intermediate is the unstable one. 35 out of 40 people are the unstable one. We're unstable under a somewhat standard adaptive Tatum-Mann process that people tend to use in this literature. Okay, so I don't know, this might mean, as I said at the beginning, this might mean that we're completely off and we're crazy, or it might mean that, and that the model is, by we are off and crazy, I mean the model. That the model is crazy, that because we are conditioning everything on the model. It might be that, or it might be that we have to think more about the dynamics. All right, so that's one thing that I wanted to say. So these are three schools, 3 examples. So the red thing is the equilibrium. So in the first school, the equilibrium is in the first, the smallest smoking. In the second is in the middle. And in the third, there's only the first. Okay? So this is the school out of 41. This is the school where there is a single equilibrium. Okay. This is what I was saying. So this is right. This has the right shape. So perhaps interestingly again, if you increase the parameter, so we can do simulations now. We have estimated everything. Okay. So J is the global interaction parameter here. Okay. So this is an example with only global. There's no local. Okay. So there's 3 equilibria. So if by increasing J, what happens is that this map flattens, and you're losing the first 2 equilibria. Okay, so what this means is that as you increase J, you might at some point lose the first 2 equilibria where the school might be, and you might jump on the highest one. Okay, so we did some experiments here again where we played with the J. One thing I should say is I'm not reporting much about the local interaction. We have estimates, but one thing that it's not that easy to do in the local interaction model, as I said, we have no closed form, so it's a little bit complicated. So from what I understand from what Giorgio tells me, the estimates are never in the range where we have phase transitions. Okay, so all the multiple equilibria come from the global J. The local J is never high enough to generate phase transition, which is good because I wouldn't know how to deal with those. Okay, or I don't know how to deal well with those. Okay, so, but this is not reported. So what we're doing is, okay, so we're playing with J's, we see what happens. Sometimes, of course, the aggregate smoking goes up, sometimes it goes down, that depends on the shape. What else do I want to say? Just 2 more minutes and I'm done. What else do I want to say? Yeah, so one thing that we do is in the case with local interaction, which in the case with global and local interaction, we simulate, as I said, we don't have closed form solutions here, so we need to really simulate the whole thing. And what we do is we do examples where we move, again, the J parameters, which is the crucial parameter here, is the parameter of social interactions. This is the global J. No, this is the local J. So it's the parameter in the utility function which says how the action of the agent depends on his small network, on the smoking behavior of the small network. Okay, so one thing which happens here, so what this line is, what the line is essentially, because to simulate this we have to run actually one of these Stratton-Munn processes, so we are losing middle equilibria here. What we do is we look at the basin of attraction of the low-level equilibria. Okay, so that's one way in which you can think about what happens if you change J. Okay, so, and interestingly enough, the more you increase J, the larger is the basin of attraction, the lower is the level of smoking at the low equilibrium. Okay, essentially the local interaction, the global too. I mean, depending on this is one particular school, but they generate correlation of smoking behavior across people. It doesn't mean that it doesn't go necessarily one way or the other. Okay, it could reduce global aggregate smoking, it could increase aggregate smoking, and this is relatively general. Okay, so the global interaction happens the same. If you increase, this is the, now change notation. This G is the J, but for the global. So you increase G, so you increase the global interaction. What happens is you have larger basin of attractions and less smoking at the low level. Of course, you might if G is very small, actually in here what happens is you actually can lose the low level equilibria and then people smoke a lot. Okay, We did number of friends, I'm done. So what do we learn? Multiple equilibria are pervasive, nonlinearities are important, at least if you stick with our model and with the solution concept. Reducing the strength of global or local interaction or the number of friends make low equilibria less likely in a lot of examples of a lot of schools for which we have estimated the parameters, and interaction might lead to less smoking.
Thank you very much.
Thank you.